We're in Rosen, Discrete Mathematics and its Applications, section 9.3 on representing relations. We're talking about the use of digraphs and matrices to represent relations, in this case, relations on a set. And here we want to illustrate how the power of a relation works. So remember that r squared is equal to r composed with r. And r cubed is equal to r squared composed with r, etc. So we can look at r squared as in relation to the original relation on our set, in this case the set A, B, C, D, that has 4 ordered pairs in it. And if I take r squared, I take r composed with r, it means I'm taking 2 steps in the original relation. So r squared is the set of all results for taking 2 steps in the original. So in r squared, if I go from A, B, and B, C, then I have AC in my relation for r squared. I have BC and CD in my relation, and so I've got CD or BD in my relation for r squared. And I have, for example, DB and BC in my original relation, so I must have DC in my relation for r squared. All right, well, similarly, r cubed will be the application of the original relation 3 times. All paths of length 3 in the original relation will be exhibited by a single arrow in R3. So if I go from AB, BC, and CD in my original relation in 3 paths, that means I have to have an arrow from A to D in my original. And then if I do DB, BC, CD, I get back to D in 3 steps. I must have a loop at D in R3. And the same thing will be true for B. Well, there's gets back to itself in 3 steps, so there's a loop in R3. And C gets back to itself in 3 steps, so there's a loop at C in R3. And now let's consider r to the 4th power. Well, r to the 4th is r cubed composed with r, and it's all the result of applying r 4 times, or paths of length 4 in r. Well, let's look at the path of length 4 from A, AB, BC, CD, DB. So the result of a path of length 4 from A is AB, which is where we started. And starting from D, there's DB, BC, CD, and then DB again. So it's just like the path of length 1. And it turns out for all of them, we get the original single step result from applying the relation 4 times. So the R4 then is actually equal to R. Okay. We can also use the matrix representation of a relation on a set to find the powers of the relation. And the way we do that is by Boolean powers of the 0, 1 square matrix. And we learned how to do that in chapter 2, to take those Boolean powers of a matrix. And the resulting Boolean power of the matrix is the matrix representation for r to the n, if we take the nth Boolean power. Let's relate that to what we just looked at in the direct graph. So here I have the matrix representation for our relation right there. And if I take r and I square it in the Boolean sense, I get this relation here that I'm double underlining. And note that it is the matrix representation for R squared. I have AC, there's AC. I have BD, there's BD. I have CB, there's CB. And I have DC, there's DC. And now if I take R squared and I Boolean multiply it by R to get R cubed, we can see that it is the matrix representation for R cubed shown on the digraph. I have loops at B, C, and D. B, C, and D have loops. And then I have the edge AD, which is also shown here. And then finally, if I take R3 and I Boolean multiply it by R again, I get R to the fourth power, which we see is exactly the same relation as the original. Okay, so that's how we can use the matrix representation to generate the Boolean a relation on a set raised to a power.